Hello everyone and welcome to another video. So today I want to continue our discussion on Fourier analysis by looking at one of, if not the most important numerical algorithm of our modern time, and that is the Fast Fourier Transform. So this is going to be a continuation of our discussion on actually the Discrete Fourier Transform. So if you haven't seen that video on the Discrete Fourier Transform, please go back, watch it. You can check it out right over here. And in fact, you might even want to even consider backing up even a little bit further. We had a discussion on Fourier series and alternate formulations of the Fourier series. So a lot of this is good foundational discussion work to get to where we are today. So what we're going to be talking about today is what's known as the Fast Fourier Transform. And I always think this is interesting to think about from a larger philosophical perspective to get the stage set. So the idea is that we last looked at what was known as the Discrete Fourier Transform, right? And we saw that the Discrete Fourier Transform is basically used to take a discrete bunch of samples in the time domain and transform that into a Fourier or a frequency domain space, okay? That one little statement is actually the basis of a lot of practical engineering and scientific applications. So the idea of the Discrete Fourier Transform, it's used all over the place. I mean, I can't even list the number of places and applications that that is used for. That idea of transferring from a time domain to this alternate frequency domain, it's used in things like filtering, convolution, image compression, video compression, audio engineering. In fact, all of the words in the video that you're probably watching right now are coming to you via YouTube, and I bet you somewhere in this chain of processing, the Discrete Fourier Transform has played a role in that application. So there are tons and tons of applications of it. Now, the thing that's interesting about it is we saw that it's given by this expression, right? The Discrete Fourier Transform, it's really nothing more than a bunch of summations, okay? The only problem is what we're going to see in just a second is that the way this is written right now, the Discrete Fourier Transform, yeah, sure, it is written down. This is the mathematical definition. You could code this up, and in fact, we will do this. But the way it's written right here, this is actually somewhat relatively computationally expensive, okay? So what ended up happening that made the idea of the Fast Fourier Transform so famous is that some really smart people that we're going to talk about in a little bit discovered a way to make this Discrete Fourier Transformation calculation take a lot less time. In fact, it can be done very quickly or very fast, hence the name. So the first thing we want to get out of the, just talk about right now is the nomenclature. So the Discrete Fourier Transform, right? That's this mathematical operation that we're discussing here. The Fast Fourier Transform is an algorithmic implementation of this particular idea, right? The thing that I want to just call out is it's become so ubiquitous, though, that pretty much everybody uses the Fast Fourier Transform, or the FFT, to compute the Discrete Fourier Transform, or the DFT. So it's been used so often that, in fact, those two terms are almost used interchangeably. So when you hear people talk about the FFT, what they really mean is they are talking about a Discrete Fourier Transform, but they're talking about calculating that in a very specific way with a very specific algorithm, right? So again, the DFT is the general mathematical idea, right? And then the FFT is an implementation of that idea into a numerical algorithm. So again, you'll hear these used interchangeably, but we just want to get that out of the way first, okay? So let's talk about this, okay? Where do we go from the DFT and get our way towards this FFT algorithm, okay? So again, in our last video, we discussed, here's the discussion, right? Here is the definition of the DFT, right? And all this thing does, we saw last time, is you're basically taking all of your samples Fn, right? And you are just weighting them against some power of this primitive nth root of unity, okay? So that's all this was, right? You could write this out. And in fact, it might be helpful to write this out explicitly. Let's get the k equals 0, 1, 2 terms, you know, all those kind of terms, just so we can get a rough idea. So this one right here, right, this first line, this is for the k equals 0, right? And you saw you can just write out this sum. Just put k equals 0 here, k equals 0 here, and then iterate from n goes 0 to n minus 1, right? So you get this expression right here, okay? Then let's do the same thing for the k equals 1, right? That's this term here. And you can go all the way down to the k equals n minus 1 term, right? Now, the thing to maybe notice in this expression, right, is there's a lot of stuff that kind of repeats or is the same, right? So notice here that really this F0 is the same here. The F0 shows up everywhere, right? And then F1 also shows up. F2 shows up the same. All the way, the samples show up consistently, right? And they show up consistently as just coefficients of this power of the primitive nth root of unity, right? And again, the other thing that shows up all the time is this nth root, this primitive nth root of unity. You see it's everywhere. It's just raised to different powers depending on where you are in this expression, right? So the only thing that's really changing in this, it's these powers, right? It's the exponents. You can actually see them right here, right? This n and k, those are the two things that are changing. So if you stare at this thing long enough, you see it's just a system of n equations, and effectively there are n inputs, right? There's these samples f0, 1, 2, all the way up to n minus 1, making up a total of n samples. So you know what? Let's write this as a matrix, right? And that's what I've done over here. You can see that you can take this series of n equations and just write them in a matrix form, okay? So this is what you end up with, right? So on this side, let's just call this vector, this is, you know, f hat as a vector. And I guess I guess I'll try to draw this in bold, right? This is just a vector of f hats, okay? Then over here, same thing, this, let's just call this a vector f. Maybe I'll put a bar on top to denote this, and maybe I'll try to draw it in bold also, okay? So these are just n by 1 vectors, right? And in between, you've got this matrix here, which is basically just all of these primitive nth roots of unity raised to different powers, right? So if you're careful, this is what you end up with, right? And you see this entire matrix, it's nothing more than all of these primitive nth roots of unity, and the exponent or the powers are just a little bit different depending on what row and what column you're in, okay? So let's call this entire matrix maybe capital F, okay? Because as you can see, it is nothing more than just an n by n square matrix, right? So the thing that's fascinating about this is we can boil down the entire discrete Fourier transform operation, right? This is just coming out to a matrix expression of f hat is equal to capital F times f, right? That's all this thing boils down to, right? And this is beautiful for a lot of different reasons, right? One, let's make a couple of observations. First off, look at this matrix capital F, right? This is sometimes referred to as the DFT matrix, right? Because it is literally encoding this entire discrete Fourier transform operation is just encoded in this matrix. And what's fun about this DFT matrix is notice that it's not a function of what the sample values are, right? The only thing this is a function of, right, if you look at our definition of the primitive nth root of unity, is that all you need is the number of samples. So the second you know the number of samples in your discrete signal, right, you can go ahead and calculate this F, this DFT matrix, right? That's one great thing. And maybe one thing I will point out while we're staring at the DFT matrix and this definition of the nth root of unity, maybe I should point out, depending on where you look, what reference textbooks you look at, some people define the primitive nth root of unity as e to the positive 2 pi I over n. And some people, you may see this with the negative sign here, okay? And if you see it with the negative sign here, you better make sure this is a positive up here in your definition. So again, it really doesn't matter how you define omega n as long as you are consistent, right? I am going to do this to be consistent with my notation that I've been using, and we're going to go like this, where the primitive nth root of unity has a positive exponent, so therefore this exponent needs to have a negative sign. But again, some other textbooks or references, you may see it switched. At the end of the day, this is, you know, if you substitute everything in, there should be a minus sign floating its way in there somewhere. But okay, that's the other side note. Okay, back to our matrix expression, right? So now that we understand what this DFT matrix is, right? It's just, I mean, you can fill it in the second you know the number of samples. You just go ahead and write out this n by n matrix. But look at this thing. Couple of observations to make. One is this entire first row, right? Look at this. It's something raised to 0, something raised to 0, something raised to... All of these entries are 1s, right? So this entire first row is 1. And then you can do the same thing if you look down the first column, right? All these are just powers of 0, right? So the entire first column as well is all 1s, okay? So you get this matrix where the first row is 1s, the first column is 1s, but everything else, it's dense, right? There's a non-zero entry everywhere, and let's just leave it at that, right? There are non-zero entries everywhere. So if you think about this, this here is basically performing the DFT operation, right? Now, if you think about this, what you end up having to do then, because this capital F is dense, right? There are n by n elements. So how many operations are you going to have to do to compute this vector f hat? You're going to have to multiply this row, this column f by this first row. That's n multiplications. Then you're going to have to do this column times the second row. That's another n multiplications. Third row, another n, all the way down to the nth row. That's another n operation. So what I'm getting at is if you count up all these operations, this operation here, this is of order n squared, right? So as n increases, the number of multiplications, the size of this matrix grows by quadratically, right? Okay, so that's one thing to note. I just want to call that out. That's one thing that we're going to have to keep in mind, right? Okay, so now that we've got this in place, this is sort of a brute force approach, right? You can totally do this. You can make this calculation, and in fact, we will code this up in Matlab, and we'll actually do it for giggles. But this is actually not a great way to go because of this scaling, right? This is unfavorable. As your problem size gets big, this is going to take longer and longer and longer in a quadratic fashion, which is not favorable. So that's going to lead now to our discussion of the fast Fourier transform. All right, so now let's take a look at a concrete example to maybe get a little bit of insight into what this fast Fourier transform or FFT algorithm is doing. So again, here's our definition of our primitive nth root of unity. And now let's consider, 8 samples. Let's say you have an n of 8, right? So the second you have the n, right, you know what the primitive nth root of unity is, and therefore you can fill in the DFT matrix as we just discussed, right? So I've written it out here for n equals 8. It took me a little while to write this, all these 64 entries, but again, you see we got a row of 1s, we got a column of 1s, and then we got a lot of stuff in here which almost looks like there are repeat terms kind of sprinkled all over, right? But in some kind of odd locations. And remember from our discussion on the discrete Fourier transform where we saw each one of these you're basically going around that complex unit circle and you're jumping by different amounts each time to get these different samples, but you basically are hitting these exact same locations over and over and over in different locations, right? So I think that's some of the insight that actually was realized by two really famous mathematicians, James Cooley and John Tukey. So these are their pictures. These are probably two of the more famous mathematicians because they made this realization that there's this structure in this DFT matrix. And in fact, you can actually even see that structure a little bit more. If we go up from n equals 8, let me show you a little movie over here of an n equals, I think, what did I put here? 512? I think this is, yeah. 512 by 512. And what I'm plotting here is, again, if you look at this DFT matrix, we see that it's a complex matrix, right? There's real parts, there's imaginary parts. So what I'm showing over here is on one side of that movie, that is the real part of the matrix. The other side is the imaginary part, just because it provides an easy, convenient way to visualize it. And you can see that there's definitely patterns, right? And in fact, you can see as I resize the image, you get these really cool kind of interference patterns showing up in the DFT matrix if you just look at it. So if you stare at that, you can definitely see this thing is not purely random, right? There is some structure underlying this. The question is, can we extract some of that structure, okay? So that is basically what Cooley and Tukey did in their very, very famous paper from 1965. I'll show you a picture of the abstract right here. Again, these impactful papers, it's funny, they're usually short. This one's only, it's a handful of pages. It's not a dissertation by any means, but buried in there is a lot of power. And in fact, if you Google search, what do people think is, some of the more important algorithms of the 20th century? The FFT, or the Fast Fourier Transform, that comes out of this paper is probably near the top of that list, if not at the very top. So this idea that they discovered and codified with this paper has, as we discussed earlier, wide-reaching impacts because it's going to allow us to compute this DFT in an efficient, quick manner. Okay, so how does that happen? To get an idea of how that happens, they made a really interesting observation. So here is the standard DFT matrix operation that we talked about earlier. Okay, right? You have a bunch of samples, F0, 1, 2, 3, 4, 5, 6, 7 in our case. You multiply it by this big matrix using this n by n operation. You get out the samples, or this in the frequency domain, right? You start in the time domain here. You get a complex set of numbers which encode frequency information about that underlying signal. Okay, so what Cooley and Tukey did is, let's say, all they did is said, okay, instead of having this vector f, what if we just reorder it? What if we take the even indices, meaning like this, the 0, 2, 4, 6, right? Pull those out and stack them on top. And then pull out the odd ones, the 1, 3, 5, 7, and stack them on bottom, right? So all we're doing here is we're just reordering the input vector, right? So it's going to look like this. So now the top part above this dashed blue line, it's the even, F0, 2, 4, 6, and underneath it's the odd, 1, 3, 5, 7s, right? So that's the first thing we got to do, okay? Now, the thing that we should think about then is, okay, if this over here, let's call this FR for reordered, right? That's all this little subscript R means. We've done nothing. It's the exact same data. We've just kind of shuffled their ordering, okay? How is that related to the original vector f, right? This vector here, okay? So I've written it over here. And as you can see, we can write a transformation matrix. Let's call this matrix here T, which goes from the original to this reordered vector, right? And you can see this is actually pretty easy to do. All you got to do is just look at this, and you can say, okay, what's this first row? F0 had better equal F0, right? So all I got to do is put a 1 in here and zeros along that whole other row, okay? Now this, I need the second row to read F2, so I actually got to jump and put a 1 right here, right? And same thing, F4, I'm going to jump, I'm going to put a 1 here, and then F6, I need this to hit this last, second to last entry, like that, right? Okay, so this is the top half of that matrix, T, and now the bottom half of the matrix is you kind of interleave the other ones. So now I need F1, so that needs to pick up the second column, so there needs to be a 1 right here, and then same thing, I'll go down and jump, down and jump, down and jump, right? So this T matrix is actually really simple to construct. It's just ones and zeros. The ones are in this sort of staggered diagonal, as you kind of see here, in 2 waves. But you can write yourself up an algorithm to do this really, really simply, right? And this matrix is really quite easy to compute, right? So what this is going to allow us to do is basically write down that, okay, I now can go from my original set of samples, I transform it through T, I can get a reordered set of samples, right? Now, what we're going to want to do is, if I want to then still be able to compute this operation and still get F hat out here, but I'm going to use FR on this side, so let's write this down, okay? So I still want F hat coming out of this entire operation, right? That's the goal. The overall underlying goal is to get this vector F hat, get this complex vector, which is the frequency domain representation of the samples, right? What I still want to do now is I want to now use FR as my input, okay? So I can't just multiply by F here. What I've got to do is I've got to reorder these rows, right? And again, reorder the columns so that they pick up the appropriate sample. Oh, sorry, I'm pointing at the wrong one. In my reordered matrix, right? And if you watched our video on elementary row operations, I think you realize that what I need to do in this case is I need to multiply this F by this transformation transpose. So I need to go T transpose, like that, right? So let's call this here maybe F reordered, because all this thing is, it's just this F matrix, but I've shuffled the columns appropriately so that they still hit the appropriate, I keep pointing to the wrong one, they hit the appropriate entry of the reordered samples, right? And again, I think you can see that this is correct, right? Because what I'm saying is at the end of the day, we have an alternate representation of that same equation over here. It's just f hat, right, is equal to f reordered times the samples reordered. Like that, right? Okay? And we can verify that this is correct by basically just substituting in the expression. So oh, sorry, there should not be a bar there, right? This is just a big old matrix. It's this matrix here. So this is just f times t transpose, right? Okay? And then what is f reordered? That's right here, right? F reordered is just t times f, right? And now you can see, okay, what is t transpose t? Well, look at t. We can easily see that this is unitary, right? It's an orthogonal matrix, so this is unitary, so therefore t transpose t is equal to t transpose, which is equal to the identity matrix, right? So this term in the middle just becomes the identity matrix, and we recover f times f, right, is equal to f hat, which is what we originally had over there. So this is correct, this is good, this is an alternative way to express that DFT matrix operation, right? So great, this is good. The only thing there is we really haven't done anything too fancy if you think about this long enough. All we have done is literally just reordered columns and reordered samples. So we haven't got away from this order n squared, right? Because this operation, it's still an order n squared operation because this FR, it's still a dense matrix, right? You still got the same number of samples. We haven't done any magic yet, right? So the magic comes into the next step. Okay, so this is where it gets really interesting. So remember, this is where we are, right? We said the Fourier transform matrix representation looked like this, okay? Now, the key here is, check this out. This matrix, this rearranged version of F, right? Not this matrix, but the rearranged version of it, that can actually be rewritten as the product of these two matrices over here, okay? Let's take a look at these, what these matrices are. So both of these things are still, this is an n by n matrix, right? But it's the whole left side of it, this is an identity matrix of size n over 2, right? So in this case, remember, n is 8, but what we're doing is we're breaking it up into now, this is a 4 by 4 submatrix here, right? Here's another 4 by 4 identity matrix. So these two things are really easy. Then you got this other matrix that we're going to call dn over 2. So again, this is also a 4 by 4, and this is a 4 by 4, okay? So as you can see, this whole thing together becomes a 8 by 8, right? So again, n is equal to 8, okay? And the only thing that's interesting on this side is these D matrices here, they're actually a diagonal matrix where all you do is on the diagonals, they are the primitive nth root of unity, right, that we had over there, raised to the power 0, 1, 2, 3. So this again, it's a 4 by 4, but it's a diagonal 4 by 4. Okay, and we should be explicit here and be careful. I want to call out and note that this entry right here, it's literally this number, omega n. In fact, let's do this in another color, right? So for n equals 8, this is e to the 2 pi I over 8, right? Or I guess you could write this as e to the pi I over 4, right? Okay, so this first entry here, it's just a 1 because it's raised to the 0. But this next entry, it's that number raised to the -1 power, right? So here you go, -1, -2, -3 power, all right? So it's a diagonal matrix, okay? That's what this one is, okay? Now, let's look at this other matrix over here, okay? This is also a n by n matrix, but it's block diagonal. This whole thing is block diagonal. The off ones, these are just 4 by 4 matrices of zeros, okay? That's what these guys are. What this thing is, what we're going to call Fn over 2, it is a 4 by 4, and what this thing is, this Fn over 2, that is nothing more than your standard 4 by 4 DFT matrix, okay? The only thing that I'm going to call to your attention, and make sure you don't miss, is that, you know, again, you got one row of 1s, you got one column of 1s. But this entry right here, this is actually the nth root of unity divided by 2, because this is your standard 4 by 4 matrix. So this right here, don't put in the red number over here. This was the primitive nth root of unity for n equals 8. You got to get the primitive nth root of unity for n equals 4 and then raise it to the appropriate power. So again, I've written it just here for completeness, right? So this you can think of as the 2 pi I over 4, right? Okay, so you raise that to the negative 1 power. You raise it to the exponents. And again, all this thing is, this is your standard DFT matrix for a 4 by 4. So if you didn't know any of this other stuff and you just had 4 samples and you computed a DFT matrix, this is what you would end up with, right? So again, that's what we end up with, right? That's what this is, okay? We make the claim that this is what happens. And in fact, we'll go to Mathematica and verify that that actually works in just a second. But I want to stare at this equation and think about what are the ramifications of this equation, right? If it is true that FR can be written as the product of these two matrices, look at what actually ends up happening, okay? Because what happens, right, is we are going to multiply FR, the reordered samples on this side, right? So in fact, let me just kind of do this in sort of a fast and loose fashion with like this. So there's FR, which was, I think we said F even stacked on top of F odd, right? So this will multiply by this will hit a 0, and then similarly in the bottom row. So what ends up happening, right, is if you look at this long enough, really, this is not a dense matrix multiplication any longer, right? What you've got to do is you're going to eventually have to multiply, let me find one more color to keep this, everything square, right? You're going to have to multiply this F even. This thing was a, you can think of it in our case, this was an n over 2 vector, right? N over 2 by 1, right? That's what this vector is. This is going to be multiplied by a n over 2 by n over 2 matrix, right? And similarly, this one down here, this is also an n over 2 by 1 vector. That's going to have to be multiplied by a n by n matrix. So really, this matrix operation that we're talking about here, each one of these purple arrows, this first purple arrow, this is an order n over 2 squared, right? It's not an n squared problem anymore. It's an n over 2. And the same thing down here. This is an order n over 2 squared problem. And then this over here, this is easy, right? It's an identity, and it's really simple to calculate, multiply by a diagonal. So this is really almost like trivial. The meat of the problem here, it's these two purple multiplications, right? So at the end of the day, what ends up happening is this, which we said earlier, this was an order big, n squared operation, right? This now gets broken down into 2 order n over 2 squared, right? So it's a lot smaller problem over here. So this is the beauty of, and if you look at this long enough, what we're basically doing, this FFT algorithm, it's a little bit of a divide and conquer, right? By just switching the indices around, you can get this decoupling and you can get this block diagonal format, and you're reducing the size of your problem. You might have 2 problems instead of 1, but these 2 problems, each one of them, are way less than half of the work, right? So what we're effectively doing, right, is we have taken an 8 by 8 DFT problem, split them into, again, this purple arrow, this purple operation, that is a standard 4 by 4 DFT problem, right? That's the exact same problem we were dealing with earlier, but we've more than halved the size, right? And the price we pay for that, of course, is we have to do 2 of them, but it's way smaller. And do you see where this is going, right? We took something from 8, we halved it down to 4. You can take this 4, halve it down to 2. Or you can go the other way around, right? This 8 by 8 problem, it might have been, this might have come from a 16 by 16, right? And that was broken up into 2 8 by 8 problems. And again, think about this again. The 16 by 16 problem, that could have been broken from 2 32 by 32 problems, or by a single 32 by 32, right? So do you see how this is sort of this pyramid scheme effectively, where you can take a large problem, as long as the samples are some power of 2, and split it in half, then take those 2, split it in half, take those, split them in half, right? So you get this pyramid structure that you can exploit, and what it buys you is a lot of this performance, right? So you know what, tell you what, let's go to Mathematica and let's show that this actually works before we keep going any further. Let's actually prove that this works. So let's jump over to the computer. All right, so here we are in Mathematica with my notes, and just for the interest of completeness, I think I want to go through this whole thing and just show everyone that that this actually works. Okay, so here we go. I'm just going to go ahead and define my primitive nth root of unity. So again, you just tell me the number of samples n, and this will just compute the primitive nth root of unity as we discussed. Okay, so that's great. Next, let's scroll down a little bit, and again, feel free to pause this if you want to copy down the code, but I just wanted to show everyone. I wrote myself a little module to compute the DFT matrix. So again, all you got to tell me is the size or the number of samples, right, n, and I'll go ahead and we will use that nth root of unity, and we will just raise it to the appropriate power. So all this module will do is you pass it the number of samples or the size, and this computes the standard DFT matrix for you. Okay, so let's keep going. So for example, for our case of n equals 8, again, I'll just use my little module I wrote, and this is exactly what we had on the board, right? This is our 8 by 8 problem, right? Okay, so let's keep scrolling. Yeah, we talked about all this already. Let me keep going. Yeah, I'm going to define some variables. I'm going to define that transformation matrix that we talked about. So again, we saw that there was an easy way to do this. Again, here's the code for it if you're interested, but it just generates a matrix of this pattern that we talked about with kind of this descending ones. So again, here's the T matrix. In our case, it's an 8 by 8, okay? And just to prove to us that this actually does work to rearrange columns, I just made a really simple, silly 8 by 8 A matrix where each row, each column, this is filled with ones, some variation of 1, then some variation of 2, 3, etc., just so that we can see that what that T matrix does is that when you right multiply by its transpose, all it does is it kind of reorders these columns, and it basically pulls in we were calling them the even indices, but that's because we were kind of in a zero-based indexing system. But you can see this clearly does. It pulls out the odd, like the 0th, the 2, 4, 6 column, and then followed by the 1, 3, 5, 7 column, right? Just reorders it. So great, that T matrix is totally working. So let's go ahead and reorder our F matrix, right? So again, we will reorder it by right multiplying by T transpose. And again, all that does is we still have that dense 8 by 8 matrix right here. This is FR, right? This is the reordered DFT matrix. And this is what we are going to claim is we can rewrite this thing, right? So again, keep this in mind. This is what we're going to have to compare it to at the end of the day. We want to make sure that we can recreate this by using these two the quasi-diagonal matrices, right? So again, all we got to do is build these up, and again, just to make sure that we don't miss anything, I want to stress the fact that again, this D matrix, this diagonal matrix, this is the nth root of unity for in our case, n equals 8, right? And then these F matrices over here, these are your standard 4 by 4 DFT matrices. So now you actually use the primitive 4th root of unity, not the primitive 8th root of unity for its calculation. So again, that's all I'm doing. Again, feel free to pause the video if you want, but here's the code that I use to basically build all of these sub-matrices. And again, this is what they look like. So again, 0 matrix, it's just a 4 by 4 of zeros. That's self-explanatory. The identity matrix is a 4 by 4. And here we go. Here's the diagonal. So again, this is using the primitive 8th root of unity on the diagonals, right? Whereas the F matrix here is using the primitive 4th root of unity on the diagonal. So we get a standard 4 by 4 matrix, right? And now all we got to do is we made this claim that if you combine all these in the appropriate fashion, you recover FR. So that's all I'm doing right here is I'm just joining all these matrices together. I'm doing the operations, and then I am just going to compute it. Given this, we claim that you can make this multiplication, this matrix multiplication of these two big sub-diagonal block matrices, right? So this was the one that had the zeros and that had the identity matrix and the diagonals, and this is the one that had the zeros and kind of the 4 by 4 matrices. And again, I'm now going to check this again. Remember earlier we said keep that in mind. This was your reordered 8 by 8 matrix. I'm just going to subtract what I got by doing this calculation, and look at this. You do get a whole bunch of zeros. So in fact, yes, this does work. This is valid, right? So this FR, we can decompose it as such, and therefore we can write this as we talked on the board. Instead of a full order n squared operation, now we're really talking about 2 order n over 2 squared operations, right? So that's great. Now, again, since we've got Mathematica up, we might as well go the other way. And I'll prove to you that this also works for if we go the other way. Instead of breaking it down by a half, we could also look at scaling it up by double, right? So I can look at a 16 by 16 problem, which again, I don't think I want to write that on the board, but I got no problem just changing a couple of variables in my code and basically going through this whole thing again. So again, here's your full 16 by 16 matrix, right? And now we can make a 16 by 16 transformation matrix, which all it does is reorder the columns. So therefore, we can reorder the DFT matrix to be a 16 by 16 reordered matrix. Then I'll go ahead and again calculate all of the, my 8 by 8 0, my 8 by 8 identity, my 8 by 8 diagonal matrix, my 8 by 8 DFT matrix, which again, we should maybe make a note, this thing that I've got highlighted right now, this is the DFT matrix we were working with earlier at the beginning of this discussion, right? So we're going to break it down into 2 of these problems, right? So again, all I'm going to now do is just verify that this all works in the exact same fashion, and look at this, you subtract the 2 and you get all zeros. So yes, this totally checks out. So again, this is super powerful and super exciting. It's how we can basically divide and conquer the problem into successive powers of 2, right? So this leads to, you'll typically sometimes see this picture associated with it, and I think now you can probably understand what is going on here. This is sometimes referred to as an FFT butterfly diagram, and you can kind of see why, but it's just talking about breaking the problem down into a smaller problem and then maybe having to interleave the results back to get what you want, right? So it's just a clever indexing which allows you to break the problem up into something smaller. And again, the thing that's really nice about this is, let me just scroll a little ways down so we don't have to go back to the whiteboard, right? Is that, what happens now is if we use this FFT approach where we divide and conquer, the operation of calculating the discrete Fourier transform is order n log n. And again, log typically in this case, a lot of times when computer scientists talk about this, we're talking log base 2. And you can kind of see where the base 2 comes from, right? Is because we're splitting each leaf of the tree in 2, right? So the FFT implementation is order n log n. Whereas the blind brute force DFT matrix operation that we saw earlier of multiplying a dense n by n matrix, that's order n squared. And again, the reason that's powerful is if you plot what does n squared look like versus n, and then you also plot n log base 2 of n versus n, look at this. As your problem grows, yeah, the savings just become enormous, right? Like n squared becomes intractable fairly quickly, right? You're not going to want to do a full DFT matrix for, 20,000 samples. But I don't think I've got any problem doing that for n log n, because you can see the red line, it practically stays flat. In fact, if I divide the blue line by the red line, I'll get an idea of the order of savings. So you can see here that this is basically a multiplication factor of how much slower the full thing is than the FFT. And you can see here, by the time you're here at, 4,000 samples, you're getting savings of 400 times, right? So for example, just to put some concrete numbers, let's look at n equals 2 to the 15, which is, 32,768, right? And that's really not a lot of samples, right? Let's say you have data that is, 32,000 samples. So for example, we talked about earlier, audio engineering is where a lot of this comes in. And most people, if you're an audio engineer, you'll know that audio is typically sampled at around 44 kilohertz. So that means in 1 second of data, you'll have 44,000 data points, right? So what we're talking about right here, this is not even 1 second of audio, right? Now, if you wanted to do an FFT on this 1 second of audio to extract its frequency content, right, and you did it using the standard DFT matrix, you're talking about a billion operations, right? Whereas the FFT operation, we're talking order of 50,000. So in this case, now you're talking about a difference of more than, 2,000 times savings, right? So that is great. And I think if you want to think about why that's happening, right, it's because this log base 2 of n, it starts to flatten out pretty quickly. In fact, I've got a plot of that right here. So here's log base 2 versus n. So you can see that, yeah, sure, maybe you don't get a lot of savings if your sample size is small, if n is small. But as the sample size gets bigger and bigger, look at this. It starts to flatten out very, very quickly. And in fact, yeah, look at this. This is nowhere near linear. So like at 10,000, this is already down to like 13. So you're getting significant savings as n gets bigger, right? So, you know what? Tell you what, why don't we actually, let's go get some audio data. In fact, that might be a good example to try this out. Let's go get some data samples from an audio source and try to do an FFT, and we'll do it in both ways. Let's use the brute force technique and time it and see how long it takes, and then let's use the FFT approach and see how long that takes. All right, so I'm sitting here at the piano. I've got my trusty audio recording device here, which is going to sample at 44.1 kilohertz. So let's just play like a middle C note, capture it here, and then take it over to Matlab and do an FFT. So let me hit go, and here, let's play the note. All right, so here we are in Matlab. I just wrote myself a little script to load in that waveform, and then we are going to pull off, let me see, what did I pick here? Oh yeah, 2 to the 12. So around 40,000-ish samples from this audio signal, which again was sampled at around 44.1 kilohertz. So let's just run this and let's just look at the waveform and the samples. So I've just plotted the samples. Whoopsie, let me grab this so you can see. Yeah, here's what they look like, right? So here's about 4,000 samples of this waveform. Again, you got to remember, these are just discrete values. I've just plotted them with lines connecting them, but if you zoom in far enough, these are just discrete samples. But you can basically see we've got a lot of interesting frequency content in this signal. So let's see if we can extract that using a couple of different methods. So we just want to use the discrete Fourier transform, but there's a couple ways we can skin this cat, right? So I've got 3 different ways to compute the DFT. So the first one here is method A, which I've listed over here. I've got this little function that does it, right? You just give it all 4,000-ish samples. This thing is just going to go and basically just compute the sum. Let me pull up my Mathematica notes where we had written this down. This is what we had up on the board, right? That's just the definition of the Fourier, the discrete Fourier transform, right? You can just basically write this sum up yourself as 2 for loops. So again, let me just kind of move this out of the way so you can kind of see. Here's the math here, and then here is the implementation. And again, it's really darn simple. Just as soon as you know how many samples you have, just compute your primitive nth root of unity, and then just loop through this thing, raising that to the appropriate power, and then multiplying by the sample weight. So again, this is pretty much implementation of that, right? That's method A. Let's go ahead and let this guy run, maybe, because that's going to take a couple of seconds. While we're doing that, let's take a look here at method B. So again, method B is just computing the giant DFT matrix, which again, I'll show you down here. It's kind of the same thing. It's just moving that double for loop to another function, but at the end of the day, we'll get an entire matrix. Okay, it looks like the first one ran. So I timed how long it took us to run method A. So for the 4,000 samples, that took around 13 seconds, right? Okay, so now let's run and see how long does method B take to execute. And I think it's going to be something similar. And then while we're waiting for that to run, let's look at our last method. Method C is Matlab has a built-in function called FFT, which is going to hopefully do the fast version of it. So again, oh yeah, here, method B finished. Method B took also around 13 seconds. Let's do a quick help on FFT. And basically, this is Matlab's implementation of the discrete Fourier transform using the Cooley-Tukey FFT algorithm or some variation thereof. So this, again, let's time it, and you're going to see this thing is lightning fast. Oops, sorry, let me hit the continue button. There we go. Look at that. Oh my gosh. not, I don't even know what that is, 0.0003 seconds instead of 13 seconds. So it's way faster. So let's just compute, and I'll show you. You get the exact same answer no matter what, right? So if you run this, yeah, look at the difference between the Matlab FFT version right here, and then method A and method B. This is like noise, right? It's so small that it's just machine problems, right? So you get the same answer. You just get it apparently 44,000 times faster than computing the full matrix. So again, this is not maybe a fair comparison because I sure as heck didn't optimize my code, whereas I can guarantee you MATLAB's FFT algorithm is optimized up the wazoo. So again, this is an illustration of, don't ever code this yourself. This is fun for an academic discussion, but just use MATLAB's FFT function. It is going to do way, way, way better, right? So that's kind of the discussion of the FFT, but since we're here and we did all this work to analyze, to get this, piano sound into MATLAB, do the FFT on it, you know what, while we're here, we might as well do like we talked about in our previous video, and let's just quickly plot the power spectral density graph of this. And again, we have a dedicated video on what this is. I just want to plot this now just so we can see, and maybe actually, in fact, this serves as a little bit of a teaser for that other video on PSDs. But this shows us both the two-sided and the one-sided power spectrum. Let's look at the one-sided spectrum. And I'm going to zoom in down to where the frequency action is. It's down here. And look at this. This looks awesome, right? So we see that that middle C note has a lot of frequency content, and there's a major power spike right here. What is this in hertz? Let's look at this. Yeah, it's apparently around 259 hertz, which I believe is about what a middle C note is. So if I just come over to Google and ask Google what is a middle C in the piano frequency here, 256 hertz. So look at this. We're pretty much right on. I mean, maybe our piano's a little bit out of tune because apparently this is picking up at around 259 hertz, but that's pretty darn close, right? So there you have it. Again, the takeaway for this lecture, the whole discussion, at the end of the day, to summarize all this, is just use MATLAB's FFT if you want to do this in a fast manner, right? So use FFT. It gets you what you want. What we saw here is that it's going to operate assuming that you have powers of 2, right? The data that you pass, it should have a length that is some power of 2, so it can take advantage of this divide and conquering. And in fact, what I believe happens under the hood is if your data is not a power of 2, MATLAB will actually pad it with zeros appropriately to get you to a close to a power of 2, so that it can take advantage of this this benefit of the FFT algorithm. So yeah, there you have it. I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. We're going to have more videos on Fourier analysis, including things like power spectrum density, talking about denoising signals. Now that we have access to the FFT, there's all sorts of things we can do to it, and we want to explore those in some future discussions. So hopefully I'll catch you on one of these future Mondays, and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye-bye.